Neutron stars are some of the most extreme and mysterious objects in the universe. Even with all our advances in physics, there is still a lot we do not understand about them. They are not black holes. They sit just before that cliff, compressed almost as far as nature allows, but not quite over the edge. In this video, we will follow a neutron star's story. From its birth in a dying star supernova, to the strange forms of matter inside it, to the violent collisions that can literally create gold. To understand how something this extreme can even exist, we have to start with a very different kind of star, one that is about to die. A massive star is dying. For millions of years, it has fused lighter elements into heavier ones in its core, pushing back against its own gravity. It used to fuse hydrogen to helium, but now the core is made of iron. An array of heavy elements surround it: silicon, oxygen, then carbon. Two light elements, helium and hydrogen, can no longer be found at the core, but in the crust. The star is running out of fuel. As fuel runs out and fusion weakens, gravity starts to win. The star tears itself apart in a titanic explosion, a supernova. The remnant of a supernova is the star's very dense core. It is now a neutron star. It packs about 1 to 2 times the mass of the Sun into a sphere only around 20 kilometers across, roughly the size of a city. That means its density is similar to the density of an atomic nucleus. If you could somehow scoop out a single teaspoon of neutron star material, it would weigh as much as a mountain. Can you hold a mountain with your hand? Inside, the pressures are so extreme that atoms look different. Protons and electrons are forced together, merging into neutrons. The entire star becomes a gigantic lump of nuclear matter, one enormous nucleus held together by gravity. That is why we call it a neutron star. Despite being so small, its gravity is extremely powerful. At the surface, gravity can be hundreds of billions of times stronger than on Earth. To escape from this surface, you would need to travel at a speed that is a significant fraction of the speed of light. This gravity does not just pull matter, it also bends light. The neutron star's gravity warps the space around it so much that light rays curve around the star. As a result, an observer can see parts of the surface that should be hidden on the far side, wrapped into view by space-time itself. So even though a neutron star is only city-sized, its mass, density, and gravity make it one of the most extreme places in the universe. Let's get a feeling for how intense that gravity really is. On Earth, gravity is strong enough to keep us on the ground, but not so strong that rockets cannot escape. To leave Earth entirely, you need to reach what we call escape velocity, about 11 kilometers per second. Now compare that to a neutron star. Take a typical neutron star, about 2 times the mass of the Sun, squeezed into a radius of only 20 kilometers. If we plug those numbers into the escape velocity formula, the result is shocking. Instead of 11 kilometers per second, the escape speed at the surface of a neutron star is around half the speed of light. This is why we say the surface gravity is hundreds of billions of times stronger than Earth's. Let's take a slow dive into a neutron star from the outside in. Outside the surface, there is a very thin atmosphere whose thickness is only millimeters to a few centimeters. The element composition inside it determines the spectroscopy result done from here on Earth. We still haven't fully understood its exact composition, but it is believed that it consists primarily of ionized hydrogen. Just beneath that atmosphere is a thin ocean of fully ionized nuclei immersed in the sea of free electrons. It's about 100 meters thick and behaves like a liquid. As we go deeper, things get even stranger. The pressure crushes this plasma into a crystal structure. The matter freezes into a solid lattice of heavy, neutron-rich nuclei surrounded by a gas of fast-moving electrons. This is the outer crust, a rigid nuclear crystal stretching around the star. Beneath the outer crust is the inner crust. The nuclei pack in more and more neutrons until they cannot hold them all, and free neutrons begin to drip out between them. The intense pressure from gravity forces the nuclei, consisting of protons and neutrons, to deform from their usual spherical shape. This results in what scientists call pasta faces. They can have long tubes like spaghetti and flat sheets like lasagna. Going deeper from the inner crust, we meet the outer core. Because the gravity is so intense, the density is much larger here. In this region, nuclear pasta dissolves into neutrons, primarily, and protons. There are a few electrons left. Most of them join protons to make new neutrons long before we reach this depth. At the very center lies the most mysterious part, the inner core. Here, our theories start to disagree. It could still be ultra-dense neutron matter with a bit of protons and leptons. Or it might contain more exotic ingredients, particles with strange quarks, condensed mesons, or even a soup of deconfined quarks themselves. Right now, observations are not precise enough to pick one clear answer, so the true heart of a neutron star remains an open question. Some neutron stars reveal themselves in a dramatic way. We call them pulsars, the pulsating radio source. A pulsar is a rapidly spinning neutron star with an extremely strong magnetic field. Its magnetic field channels charged particles into narrow beams of radiation that shoot out from the magnetic poles. Those beams can include radio waves, X-rays, even gamma rays. If one of those beams happens to cross Earth, the pulsar appears to blink on and off with a regular rhythm. By timing these pulses with high precision, astronomers can study the extreme gravity and magnetic fields of neutron stars, test theories of spacetime, and even use pulsars as natural cosmic clocks scattered across the galaxy. Some neutron stars orbit each other as a close pair. As they orbit, they slowly lose energy by sending out ripples in spacetime called gravitational waves. This makes their orbit shrink, so they spiral closer and closer together, moving faster with every turn. In the final moments, they are whipping around each other many times per second. Then, in a fraction of a second, they collide. The crash tears off chunks of neutron-rich matter and flings them into space at a significant fraction of the speed of light. This creates a brief but incredibly bright explosion called a kilonova. Inside the ejected dust, nuclei rapidly grab neutrons and build heavier and heavier elements. This is where many of the universe's heaviest elements are forged: gold, platinum, and others. By watching these collisions, astronomers can learn about the mysterious matter inside neutron stars, and at the same time, see how these dead stars help build the ingredients for new worlds. Don't forget to hit that subscribe button so that you won't miss our next content. Do you think that there is an object much weirder than neutron star? Let me know in the comment section. Thank you, and see you next time.